Alright, let's get started. So hello everyone, this is SeungryongKim. So today we will start the 3D computer vision part. So this is Lecture11. So this week and next week we will talk about what 3D computer vision is. Okay. So before that, based on your previous opinion, we will increase the paper single time as 10 minutes per paper and reduce the code review time as 10 minutes per paper as well. So paper plus code will be the 20 minutes, okay, within 20 minutes. And okay, let's start. Okay, so before that, before starting, is there any question for our for the presentation, student presentation? I guess this week and next week we will see so many papers about 3D computer vision, and before the final exam, maybe we will have one more topic. So, which means you don't have the enough chance to present your presentation. Okay, so please keep in mind. Okay. 네, 재원 학생. 네, 다음 주 발표예요. 이번 주는 오늘 이런 강의만 해도 좀 시간이 촉박할 것 같아서 다음 주에 하면 될 것 같아요. 알겠죠? So, right. So where right now? So, starting from this semester, we started with object segmentation or the detection. This is kind of the 2D recognition, right? As we can see in previous papers, 2D recognition, for example, segmentation, prompt segmentation, or detection, or instant segmentation works very, very well. Very, very well, right? As you can see here. But the premise is we live in a world that is 3D. So, in other words, although we see in 3D space, what I actually see is always 2D projection. Even though we are lived in the 3D world, when we take a picture, it's going to be the 2D projection from the real 3D world. So it's going to be the 2D images. So in these 2D images, we may lose some kind of geometry information from the in the 3D world. So learning for the 3D vision means we want to recover or we want to discover the missing 3D information or the 3D geometry information from the projected 2D images. This is the 3D computer vision or the learning for the 3D vision. So why this 3D information is useful, not only in the computer vision part, but also other kinds of application. So one of the most important application is a self-driving car. So for example, the depth estimation from the camera or the LiDAR sensor, and the 3D human modeling in a CCTV or the other your video, or the 3D reconstruction by using the multiple images or the infinitely many images. This is kind of images, right? For example, SLAM or the SFM, MVS. And 3D object detection is another one. 3D object detection is aims to infer the 3D object box from the 2D images. And then there are broad applications that benefit from the 3D data. For example, robotics. Of course, to understand the geometry, we need a 3D computer vision. 그렇죠? That make a robot understand our world, right? Augmented reality and the virtual reality is another applications. 그렇죠? We want to recover the 3D world, and then we want to find out matches between real world and 3D world, virtual world, or the augmented world. Autonomous driving is another one, and the medical imaging, of course, such as like CT or MRI construction is another medical image application. Okay. Anyway, there are so many kinds of broad application. In 3D learning task, there exists the richness of the 3D learning task. For example, 3D synthesis part, we can reconstruct the 3D monocular 3D construction or the shape completion from the imperfect the 3D models. We'd like to reconstruct or complete the 3D model like this, or we want to classify this 3D model as a, in this case, part segmentation in the 3D world, not a 2D images. So this is the 3D synthesis perspective. In 3D analysis perspective, we can detect the 3D object in looks like this in the 3D space, or we can classify 3D representation or the segment, or we can find the correspondence field, not a 2D image as we discussed the previous week. We can find the 3D correspondence field between the 3D, two kinds of 3D representation. In this case, two 3D humans. These kinds of correspondences. Anyway, there are so many richness of the 3D, so much richness of the 3D learning task. So today we will talk about so many kinds of way to reconstruct or discover the 3D information from the 2D images or video. First of all, 3D information acquisition. So roughly, we can say that there are two kinds of way to acquire the 3D information: active sensing and passive sensing. Active sensing means using an infrared to sign the patterns of the individual dot and measure the distance from the sensor. For example, like the Kinect, Microsoft Kinect, or the LiDAR sensor, or the TOF, one of them. This is based on the hardware sensor. So in general, it is very, very expensive, and many cases you have limited sensing ranges. If we consider the Kinect camera, it is very vulnerable to the illumination condition, because we cannot use this kind of Kinect or TF camera in outdoor, because it is very, very sensitive to the illumination condition. So it has a pros and cons. Another 3D information acquisition technique is the passive sensing. Passive sensing means we can find out 3D information from the multiple images or single images. So this is the passive sensing technique. For example, from the images by stereo camera, or the for example Z or real sense, by finding the depth correspondences across stereo images, we can find the depth information as we discussed last week, right? So this is one of the passive sensing way. So we can roughly, there is two kinds of way to estimate the 3D information. In computer vision, we mostly talk about this passive sensing, how to estimate your depth information from the images or the video. This is tonight's topic. So before starting, let's discuss the traditional 3D computer vision and modern computer vision, modern 3D computer vision. Traditionally, 3D computer vision was based on the physics, was based on the multi-view geometry. What does it mean? So given a 3D scene, in traditional 3D computer vision, we required multiple images taken under different viewpoint, and by using multi-view geometry in a manner that different view images see different perspectives of the same scene, and based on this based on this fact, traditional 3D computer vision develop the algorithm to find the correspondence field or to find out Q from these kinds of multiple images. So this is a traditional 3D computer vision. But nowadays, recent 3D computer vision more focusing on knowledge-based learning. In other words, similar to the other computer vision tasks, 3D computer vision try to learn prior knowledge of the 3D world in a machine learning manner. So in other words, in modern 3D computer vision, we want to find the mapping function from the images to the 3D world. And then we can find out 3D world in testing time by using this mapping function. This is the knowledge-based learning or the learning-based 3D computer vision. Learning for 3D computer vision is one of the most popularly used topics in the 3D in computer vision field. For example, when we check the CVPR 2019 submission top 25 keywords, at the time the detection was the top and 3D. Keyword 3D was the second top. And segmentation, we already discussed detection segmentation. But also earlier, we did not discuss video yet, and recognition, visual estimation, semantic, blah, blah, blah. But 3D was the second top, right? So which means the learning for 3D computer vision is one of the most important issues in computer vision. So you have to study this 3D computer vision in this semester. So to understand 3D acquisition or the 3D computer vision, we have to start 3D representation. What kinds of 3D representation we can use? In fact, there are many kinds of 3D representation. For example, 0.5 dimensional or the depth information, for example, like this, or volumetric information, for example, explicitly volumetric representation or implicitly volumetric representation, explicit volumetric representation, implicit volumetric representation, or point cloud or meshy representation. So today, let's talk about each representation first. Okay, so we want to start from here. So first 3D representation is point cloud. So point cloud is one of the popularly used in traditional 3D computer vision, popular used representation in 3D in traditional 3D computer vision field. In this representation, we want to represent the 3D as a collection of the 3D point. For example, set of x, y, g. Set of the x, y, g. So in other words, so size of our point cloud is going to be n by d, where n is the number of the point and d represent the space of dimension. In this case, in 3D computer vision case, d is equal to 3, right? And in this representation, we can represent the 3D as a sparse 3D location. It can be usually in the high dimensional space. Benefit of the 3D point cloud is that well suited for the structure from motion, and this is very, very compact representation of the sparse key point representation. For example, like this. So this is SFM. We constructed the 3D field. This is compact representation. We can adjust the memory of this representation by adjusting this number of points. And order the point cloud carries the semantics. For example, when I consider this point cloud as a key point, or the semantic key point. For example, first point represent the head, the second point represent the neck position. Then we can explicitly give semantic information as well from this point cloud information. Drawback is unstructured and not well suited for the convolution. So as we already know, to apply the convolution, we require regular representation, for example, images or pixels. So in 3D point cloud, we cannot directly apply the 3D convolution operation, and there's no orientation information. So the information that we can achieve in point cloud are very, very limited. Anyway, nevertheless, the 3D point cloud is one of the popularly used representation. And in CBPR 2017, there was the PointNet, deep learning on the point set. So in this paper, they first proposed, starting from the given point cloud, they proposed the MLP, or the fully connected network-based method to understand unstructured point cloud for the 3D point cloud classification, or the part segmentation, or the semantic segmentation in the 3D domain. It was the PointNet. And another 3D representation is surface meshes, or the mesh. This representation required edges between the point, 3D point. As you can see here, so each node represents 3D position x, y, g, and then we required edges between point, which allows, which provides the structured 3D information to us, right? Compared to the 3D point cloud. So the size of the mesh is going to be m by d, similar to the point cloud, plus e by g. E means the sum of the edges, the number of edges. The benefits of the surface meshes are good for single and multi-view reconstruction, and it provides the orientation information. For example, as you can see here, based on the edge information, we can determine the orientation of each surface. Looks like this, which provide the surface normal. Okay, I will show this surface normal later, but surface normal is the orientation information of each plane. And graph convolution can be used in the surface meshes. Of course, we can apply the graph convolution in the point cloud as well, but in general, to understand the 3D mesh information, graph convolution is usually used. Drawbacks are irregular structures, number of neighborhood and number of edge length and the face area are very varied, and it is difficult to change topologies. If we have these surface meshes, topologies, this edge information is already determined, so it is really hard to change this topology information. So shape change is required to create a new vertex and edges, which in turn provide the additional computation burden. Yeah, it was the meshes. Another representation is the voxel representation. Idea is 3D tensor, similar to the 2D image. Image was a 2D tensor. Impact the 3D tensor because HWC, C means the color, right? But in box representation is the general 3D tensor that encodes occupancy. Occupancy means binary values that denote the cell occupied, the cell is occupied or empty cell. For example, this is kind of images, right? But when it comes to the voxel representation, in this case, 32 to the 3, so x, y, g, we divide this space as a bins, tensor bin, for example, 32 bins by 32 bins by 32 bins. So we can get each, how to say, block, 3D block. Then we can assign occupancy on each block, occupied block or occupied cell or the empty cell, something like this. Then we can represent 3D information by using this kind of technique. So as you can see here, the size will be very, very huge, right? The size of our box representation is going to be C by D by H by W. The C means the channels of the each box, I mean each cell, let me say cell or block. And T means the depth, H means height, W means width. Benefit of this box representation, we can apply the 3D convolution comparing to the 2D convolution in the 2D images. Looks like this. So this is a more structured way to understand your 3D information. The drawback is the straightforward because it is the cubic in memory footprint, so computation complexity is really, really huge. So anyway, so this voxel representation is a well-structured information, well-structured representation we can understand, to understand, right? So after that, to overcome this box, the drawbacks of box representation, I just skip the batches size. So if we want to divide, if we want to divide this, how to say, this tensor as a batches, I mean the n batches, it's going to be the n by d by h by w if we ignore the channels. But usually, in general case, we have the channel in the box representation. But if we just set the c is equal to 1, so and if we have the n batches, each size of this box representation is going to be n by d by h by w. Okay. Another representation is side distance field, which is designed to overcome the drawbacks of the box representation, dubbed SDF. Idea was very, very simple. So similar to the box representation, in SDF, we want to encode occupancy information or the occupancy information. Input, in this case, input is gonna be just the dimension equals to the dimension of the space. Okay, so if we consider the 3D space, the input is going to be x, y, g. Then we want to model the mapping function between x, y, g to the scalar value. Scalar value means negative for the inside object, positive outside. For example, if we consider the 2D images, And if we want to represent your 2D object, given XY coordinate, we want to assign scalar value, which means negative inside object and positive negative outside. So this mapping function, let's say f, is assigned this function based 3D representation. There are two kinds of things. The first one is continuous SDF, defined as parametric network. For example, like mixture of the Gaussian or the neural network. Neural network means which takes the XY or XYG as input and generate this occupancy information as output. Discrete SDF means we just define on a discrete grid, looks like this, and just assign occupancy values on each grid. It is easy to display SDF in color code, for example, like this, but it is non-trivial to reconstruct the exact shape boundary, as you can see here. But comparing to this box representation, we can represent any 3D world by only using some kinds of mapping function f. We can just guess this is going to be alternative solution to high dimensional 3D space. It was the SDF. And after that, there was an innovative representation, implicit functions with a neural network. In fact, implicit functions with a neural network is similar to the sine distance field. Idea is that train a neural network, take an image as well as the 3D coordinate point as input, output, negative for the position inside the object and positive outside the object, similar to the SDF. Then by using this neural network, we can reconstruct by densely sample and Martin-Cube algorithm. We can formulate this mapping function, looks like this, f of x. F of x is occupancy output, positive within the object whole, and in general, it's going to be the CNN with the parameter theta, and x means a 3D coordinate point, for example, like x, y, g, and I means image to reconstruct. So this idea was started in this paper, FIFU, pixel align the implicit function for the high resolution cost the human digitalization. So in this paper, they tried to learn the neural network which take input images as well as a 3D point and generate the 3D occupancy field. Then by using the handcrafted Martin-Cube algorithm, we can reconstruct the meshes or the textured images, textured 3D information. Advantage of this representation, from this paper, we no longer require the explicit 3D representation. In other words, we no longer require no explicit limit on the resolution, such as done in the box representation. Only limited by the neural network capacity, which is relatively small, smaller than the box size. This advantage is reconstruction require many network evaluation. So it means that to reconstruct this 3D occupancy field, we have to feed forward each point, each XY point through the network, neural network. So it's going to be very, very small. Anyway, it was an innovative paper. So after this paper, we finally got a NERF, neural radiance field. which is the topic of today's lecture. As you know, oh, so by the way, is there anyone who first heard about the nerve or the neural ledgers field? 자, 이제 여러분들 결국 이제 여기까지 왔어요. 사실 오늘 제일 중요한 얘기를 할 건데, 널프라고 하는 거 결국에 뭐 옆에 여러분들이 아마 포인트 클라우드나 메쉬 뭐 이런 얘기 많이 들어봤을 거예요. 근데 이제 현대 3D 컴퓨터 비전에서 가장 중요한 레프렌테이션 반화가 이제 바로 임플리시트 펑션 기반의 어떤 3D 레프렌테이션이고, 이제 그게 바로 이제 널프라고 하는 어떤 하나의 모델로 왔죠. 2년 정도 전부터 왔죠. 그렇죠. 뉴리티 아니죠. 2020년도 널프라고 하는 이름으로 처음 발표되면서 이제 3D 컴퓨터 비전에서의 어떤 3D 레프렌테이션 중에 가장 강력한 방법 중에 하나로 이제 이러한 nerve or the implicit representation 이 자리를 잡아오고 있죠. implicit representation. So we will talk about this nerve today. Before that, is there any questions so far? 자, 여기까지 좀 빠르게 왔는데 혹시 여기까지 질문이나 아니면 좀 이해가 안 되거나 아니면 혹시 뭐 널프라고 하는 걸 처음 들어봐서 조금 어려울 것 같다 하는 사람 있으면 손 들어보시죠. 손은 못 들고 한번 네. 다 들어봤죠? 널프라고 하는 거? No? 오케이? 네, 학생 질문부터 가면은 knowledge based learning과 print and learning 뭐 사실 차이가 있지는 않는 것 같아요. 그냥 러닝 기반의 방법이다라고 그냥 이해를 하면 동의어라고 봐도 무방할 것 같아요, 나연 학생. 그 현대의 3D 컴퓨터 비전은 뭐 똑같죠. 모든 분야들 마찬가지인데 러닝, 어떤 knowledge를 3D Q를 러닝을 통해서 배워오는 라고 하는 게 가장 크다라는 거고, 그게 왜 중요하냐. 물론 현대 3D 컴퓨터 비전도 현대 3D 컴퓨터 비전도 당연히 지오메트리 지오메트리 컨스트레인에 기반을 하긴 하죠. 뭐 스테레오 매칭이나 멀티브 스테레오 매칭. 근데 왜 널리지 기반의 3D 러닝이라고 하느냐? 그러니까 널리지 기반 러닝을 하냐면 결국에 모노큘러 뎁스 에스티메이션이라고 하는 분야 때문이에요. 이제 우리가 오늘 강의에서 얘기하겠지만 이제는 싱글 이미지 한 장만을 가지고 어떤 지오메트리를 기반한 게 아니라 싱글 이미지 한 장으로부터 그냥 어떤 날리지에서 3D를 인식하는 기술들이 이제 어떤 현대에 훨씬 더 많이 연구가 되고 있기 때문에 그렇게 표현을 한다고 이해해 주시면 돼요. 맞죠? 정원 학생. SDF가 자리가 안 되는데 다른 뷰에서의 3D 정보는 알기 어려운 건가요? 자, 한 번 더 설명해 줄게, 한국말로. 자, 사실 SDF 이 implicit function with a neural network and 널프가 사실은 개념은 거의 다 똑같아요. 사실 이러한 개념이 결국에 복셀 레프렌테이션에서 가지고 있었던 이 문제를 어떻게 해결할까라고 하는 거에서 기반하는 거죠. 결국에 우리가 알고 싶은 어떤 3D 좌표, X, Y 좌표가 있을 때 우리는 이 X, Y 좌표가 아큐판시, 즉 채워져 있냐 안 채워지냐를 알고 있으면 우린 3D를 표현할 수 있는 거잖아요. 그렇죠? 근데 이렇게 이걸 그리드로 나눠서 이렇게 표현을 하고자 하니, 디스크라이브 표현하고자 하니 너무나 한계가 많은 거고, 이런 SDF에서 하고 싶은 건 뭐냐면은 그리드마다의 이 어큐펀시를 모두 다 외우기는 어렵지만 이 그리드의 위치 정보, 3D인 경우에는 이 XY 좌표만 알려주면 이 좌표의 어큐펀시가 얼마다, 이 좌표는 정말 그 3D 물체가 있다 없다, 그렇죠? 3D 물체가 채워져 있다 안 채워져 있다, 그 아큐판시만 뱉어주는 이 펑션 F만 가지고 있다면, 그렇죠? 물론 F라는 매핑 펑션은 이러한 모든 필드를 외우고 있는 것보다, 여기 복사처럼 외우는 것보다 훨씬 더 쉘로우한 네트워크로 가정을 하는 거고, 모델이라고 가정하는 거고, 그 F가 있다면 우리는 어떤 3D 필드를 다 표현할 수가 있다는 거죠. 즉 정원 학생의 질문처럼 다른 뷰, 어떤 뷰도 상관없이 결국에 우리가 리컨하고자 하는 3D 필드는 어떤 캐노니컬하게 하나의 스페이스에 존재할 테니까 그 스페이스를 모두 다 표현할 수가 있다는 거죠. 이 매핑 펑션 하나로. 그게 바로 SDF라는 개념이었고, 그게 이제 뉴럴 네트워크로 정립되어 온 게 바로 이제 이 논문이라고 볼 수 있는 거였고요. 이게 이제 널프라고 하는 개념으로 이제 우리가 정립이 된 거죠. 그렇죠? 혹시 이해가 됐나요? 정은? 네. 네. 혹시 좀 좀 질문 있으면 좀 더 주고 우리 아마 이제 널프는 우리가 뒤에 후반부에 더 자세히 배울 거니까 일단 간단히 넘어갑시다. Okay? So, NERF is extending this impression representation concept. So, what they want to do, they want to learn mapping function to model radius field. They call the radius field, which means taking every place or every place, in this case xyg position information with the direction, I mean the viewing direction like this. Then we want to design a mapping function that generates the output radius. Radius means outgoing light. In this case, here in RGB space. What does it mean? By taking x, y, g coordinate and during direction, we want to design a neural network that generate RGB and occupancy information at this position with this direction. This is the neural radius field. In other words, by using this kind of F theta, I mean the neural network, we can represent any kind of 3D continuous and infinitely high dimensional 3D space only with this kind of neural network. And then if we can model this color and occupancy information by using the somehow rendering algorithm, we can render the 2D images on given view. Then we can not only reconstruct the 3D information but also achieve novel view synthesis. So this is a NERF. We'll talk about this in detail later. So anyway, this is kind of the 3D representation technique. Is there any question? 준서학생, STF representation은 메쉬 안쪽 방학도 배우는 것이고 메쉬 안쪽 배우는 것이고 impulse function representation, 메쉬 surface curve 아니야. 둘 다 그 뭐예요? 그 메쉬가 결국에 그 포인트라고 하죠. 사실 엄밀하면 메쉬보다 포인트 컬러도 맞는 것 같은데 그 포인트 x, y, z 값의 아큐펀식이 변한다는 측면에서는 둘 다 동일하죠. 그렇죠? Is there any question? No? 시간이 많이 지났는데요. 네. Okay, so this is kind of 3D representation. So first of all, let's talk about 2.5 dimensional representation, which was which is called depth information or the surface normal information. So in fact, this is the 0.2 dimension because we can't find out full 3D information. I mean, we can't find out Euclidean 3D point, but we just find out 3D information at viewing direction. I mean, the input image direction. So this is a depth information. Depth map means per pixel depth or disparity map. So we have to find out corresponding depth information per each pixel. Normal map is going to be the normal values per each pixels, HW3. Output space should be aligned with the input images. So it means that we can apply the fully convolutional network to find out depth or normal information similar to the semantic segmentation technique or the task. So it is not suitable for the 3036 view lenders because we do not have the occluded information, and we can think of each pixels as a colored point cloud. In other words, with the depth information, we can find out x, y, g structure information, and we already know corresponding or GB values. So with this information, we can represent the colored point cloud, even though it just represents the partial point cloud in the 3D domain. Anyway, so this is the 2.5 dimensional representation. So from now on, let's talk about how to represent this depth information. Okay, is there any question? Okay, so before keep moving, let me take a 10-minute break and okay, 50. Let me start 251. 오케이? 자, 우리 10분만 쉬었다가 우리 51분에 다시 시작합시다. let's continue. So, to understand 2.5D 3D implementation, 2.5D implementation, we have to consider, we have to study camera geometry. There are three important coordinate system. Vertical coordinate. The vertical coordinate means real 3D world. We can set virtual 3D coordinate x, y, g here, and another coordinate is a camera coordinate. So if we have the camera here, there is another coordinate comparing to the world coordinate. So let's say this is u, v, w, right? And final one is the image coordinate. Image coordinates mean 2D space. So we have to consider this image plane, which is our given images. So there are three coordinate systems. So the question is, how do we project the given world point x, y, g to the image point? In other words, what is the mapping relationship between x, y, g to the input images, 2D images? This is the camera geometry. So how can we find out this correspondence? So to this one, we have a three coordinates. So we have to project. We have to project the one of the point in the world coordinate to the camera coordinate to the image coordinate. So first of all, even though this is the same point in the world coordinate and camera coordinate, because they have the different kinds of coordinates, so we have to change this x, y, g in world coordinate to the x, y, g to the camera coordinate. So in this case, we have to consider the extrinsic camera pose, the extrinsic parameter R and T, which explain relationship between this world coordinate to the camera coordinate. Even though world coordinate is the fixed, but camera is moving, so this relationship will be the changes. So this is the extrinsic parameter, and this camera coordinate x, y, g, we have to find out image coordinate position x, y. This is related by camera internal parameter. So this is modeled by intrinsic parameter matrix K. So by using the extrinsic parameter and intrinsic parameter, we can find a mapping relationship between the world coordinate point to the pixels in the images. In other words, to project the point x, y, g in the world coordinate into camera, first transform the x, y, g into the camera coordinate by using the extrinsic parameter. And so camera position and camera orientation, then RT, RT예요. Then project into the image plane to get a pixel coordinate. Now in this case, we have to know the intrinsic parameter. Then this is the 3D acquisition process. In other words, if we want to find out depth information from the input images, we have to think reverse process from x, y, g to the x, y value, or x, y to x, y pixel value to the x, y, g. In this case, g is going to be 3D depth values. So this is a 3D equation pipeline. How can measure? how can I measure the 3D 3D information? There are so many kinds of way to estimate 3D information. For example, star matching, photometric star matching, multiple serial, SFM, SLAM, so on. So one of the simplest one is to view star matching or just shortly star matching. So what was the star matching? What was the star matching? Given an input left and right images, as we discussed previous lecture, each pixel has a corresponding pixel in the right images. Then the displacement between these pixels and the corresponding pixels in the right images can encode the disparity and depth information for these pixels. So in this case, by considering the search lane and measure the similarity between the reference pixels and the candidate pixel, we can measure the similarity map. For example, like this, it's going to look like this. If we consider another pixels, we can get another similarity vector. By considering the whole pixels, we can achieve the tensor representation, which is called the cost volume. And by finding the minimum pixels, the pixel that have the minimum cost, we can say that these pixels, this displacement from the reference point to the candidate point, it's going to be the disparity. So when we color coded this disparity map, because this disparity map is a 1D h by w by 1, it's going to look like this. So in color coded representation, so the brighter the closer object is, looks like this. So this is this disparity map, and by using this disparity map, you can render this 3D information, looks like this. So this is the stereo matching. Of course, in deep learning area, there was so many kinds of paper to formulate this stereo matching pipeline in a deep learning manner. So the question is how to measure the similarity between the reference pixels and the candidate pixel or query pixel. So in last week we discussed the disconnect, right? And there was many other technique. So it was the MCCNN, and this is the GCNet, which is using the 3D convolution on the cost volume. This is stereo matching. We'll skip this one very shortly because we already talked about this one. In detail, so 3D stereo matching pipeline consisting of the matching cost computation. For example, our left and right camera, right images consisting of H by W, and matching cost computation generate the matching cost, which consists of H by W by T. T means a search range, and then pick the best in matching cost selection. Additionally, we use the cost aggregation or the regularization, where we regulate the nearby pixel have the similar depth information. Finally, we achieve this disparity map, which consists of H by W. This is a stereo matching pipeline. This stereo matching is the very first because it tries to resemble the human eyes, human eye process. But because this is only based on the matching between left and right images, there are many challenges and textual-less regions, like this, or the illumination variation, because even though we take left and right images simultaneously, due to the many factors, for example, the camera setting or something like this, there may be illumination variation between the left and right images. And occluded pixels is another issue, and refracted lesion is another challenge. Even though these challenges should be corrected, term matching is one of the simplest way to recover the 3D information. This two-view stereo matching method is directly extended to the multi-view stereo matching problem. Problem setting is like this. We have a, let's suppose that we have a calibrated images from the several viewpoints. Based on the assumption that we have an intrinsic and extrinsic parameter, then we want to achieve 3D object model. 3D object model. This is the 3D multi-view stereo matching problem setting. So this multi-view stereo setting can be formulated similarly similar to the two-view stereo matching. So basic idea is like this. So let's suppose that we have a 4 view images, 1, 2, 3, 4. They take a same scene at different viewpoint, and given reference viewpoint, let's say first images is a reference view, and remaining images can be the nearby view images. So in multi-view stereo matching, similar to the stereo matching, we can say that for each pixel in the reference view or reference images, there exists corresponding pixels in nearby views. Then by finding these corresponding pixels across the nearby view, from reference view to each nearby view, we can find out depth information for this pixel, this target pixel in the reference view. In other words, evaluate the likelihood or the probability of the geometry at the particular depth for the particular reference patches. For example, if we want to depth for these pixels, by considering the camera pose difference between the reference view to the nearby view, we can find out corresponding pixels at particular depth, like this. And then by changing this depth information, we can consider another pixels in the nearby view by aggregating the similarity between reference patches and the nearby view patches. We can achieve the more accurate corresponding disparity or the depth compared to stereo matching, two-view stereo matching. So in other words, given a particular depth, we have to answer patches, the similarity patches from the reference view and corresponding patches that depth gets in the other view, like this. So the question is, how we measure the similarity between these patches and nearby view patches. This is the problem setting for the multi-view stereo matching. So similar to stereo matching, by increasing the depth or the disparity, in stereo matching, it was the search range because it was search range, but in multi-view stereo, we generally say depth, right? And by increasing the depth, we can measure the similarity or the cost at this pixel. And by picking the best value, we can find out depth for these pixels. And by considering the whole the pixels in the reference view, we can find out corresponding 2.5 dimensional depth map at these reference view images. This is the multi-view stereo match. The question is how to measure this error, or how to measure this similarity between reference patches and the nearby other patches. This is multi-view stereo matching. Advantages: we can match windows using more than one other images, which gives stronger matches signals comparing the two-view stereo, because in two-view stereo we just consider the one other images, so one right images, but in multi-view images we can consider the more view images, so which gives the stronger matches signals, which help to estimate a better 3D information or the depth information. If you have a lot of potential images, we can choose the best subset of the images to match it for reference images. In other words, if we consider left and right images only in stereo matching, to be stereo matching, we may not consider occluded pixels, but if we have the lots of the potential images, we can choose the best subset of the images to handle the occluded pixels, because in some viewpoint images, they maybe take occluded pixels, so we can use the best subset of the images to find out depth information. And we can reconcile depth for each reference frame and merge it into the complete 3D model. So in other words, so we can find those 2.5D depth map when we set these images as a reference view. Similarly, we can set this one is reference view, this one is reference view, this one is reference view, and then we can merge this depth map, 2.5 depth map, to achieve the complete or full 3D model. So this is the multi-view stereo matching. So this is examples of the stereo matching by using the deep learning method in deep MVS in CVPR 2018. So first of all, given the multi-view images, first of all, we have to know the extrinsic parameter between the camera. So first of all, we have to use SFM, structure from motion, to find out camera extrinsic parameter relationship, or the camera pose relationship between arbitrary two images. Then we view cost volume by considering the reference view and one of the other images, so we can make a multiple cost volume similar to the stereo matching. And deep MVS, or the deep learning based method, we just aggregate it, hold the cost volume, and finally achieve this very map given these reference view images. This is a deep MVS stereo, or the deep MVS, or the multi-view stereo based on the deep learning technique. So this is this example by using this deep MVS. This is the depth map for the given reference images, and this is the rendered images. Because we already know depth information, we can transform this depth map and color images to the full 3D world, and by manipulating the viewing direction, we can render the novel view, something like this. something like this. This is the rendered images. Rendered image. Question. 자, 여기까지 질문. 뭐 제가 사실 뭐 좀 우리는 조금 뒷부분에 좀 더 힘을 쓰려고 우리 뭐 시간이 많이 없으니까 제가 뭐 그냥 컨셉적인 얘기만 하고 앞에는 계속 넘어가고 있어요. 그렇죠? 그래서 우리가 조금 너프라든지 최근 뭐 모노큘러 뎁스 에스티메이션과 같은 좀 소타 기술들에 조금 더 집중해서 보기로 하고 여기 앞에는 좀 빠르게 넘어갑시다. 알겠죠? Question. No? Okay. Another way to reconstruct the 2.5D depth information is photometric stereo. Photometric stereo. The problem setting of the photometric stereo is like that. Given a single static camera, in this case, we do not use the geometry by using the multiple camera, but with a single camera, we will use multiple light direction. For example, like this direction, this right direction, and this right direction. And by considering the shape or shadow from the multiple light, we want to find the surface normal or the depth information given a single camera image. This is called photometric stereo. In other words, okay, so for example, given a static images with a static camera, by manipulating the right bulb view, something like this, or this direction, maybe this direction, or this direction, right? So, and we take pictures like this. So these output images highly depends on 3D shape, like here or here or here, right? So by considering this pixel level relationship, we can find the structure information for each pixel like this. In other words, if we consider pixel values at fixed point, this one, and this one, we can estimate this structural information. This is the photometric stereo. This is examples. This is examples of the photometric stereo. So with a fixed camera, by using so many kinds of light bulb, we simulate the light source changes, and by using the images, we finally recover 3D information, surface normal information, and 3D depth information. It is very well known that compared to the other multi-view stereo or the two-view stereo, photometric stereo can help to find out fine detail the 3D information, something like this or something like this. So this kind of technique has been used in application where we want to find out fine detail the 3D representation in constrained setting, because we require the constrained setting like this, but the quality of the reconstructed 3D quality is much better than other multi-view stereo or the two-view stereo, as you can see here. This is a photometric stereo matching wizard. But nowadays, many 3D computer visions move to the learning-based framework. In other words, if we can find out mapping function between the pixel value to the semantic segmentation, semantic label in semantic segmentation. What about depth estimation? In other words, if we can find out mapping function between the color pixels to the depth values, given large scale ground truth RGB D dataset, RGB and depth paired dataset, we can learn the mapping function between depth to image to depth, then solve the monocular depth estimation. Monocular depth estimation. This is examples of the depth map, estimated depth map from these single images. This kind of single images. As you can see here, comparing to the previous two-view, multi-view, and photometric stereo. In this case, we just only consider the single images, but as a human like us, the network can find out 3D cues from the distinct images and find this depth map without any other images or any other different light or light condition images. This is also called monocular depth estimation. So it looks like this. So one of the state of art for monocular depth estimation is formulated with transformer, similar to the other computational field. So this is published in DBPR 2021 Vision transform for the dance prediction. How they do that? Similar to the semantic segmentation. Of course, this paper also solved the semantic segmentation as well as the depth estimation problem. So they consider encoder and decoder, similar to the other prior work. And they formulate this one with a transformer. So first of all, they divide input images as sub windows and embed each pixel, each patches as 1D vectors. And by using the Vision transformer or the transform encoder, we model the affinity or the relationship between the each pixels and each tokens, right? Then by using multiple transformer, and then we can decode this encoded transform feature vector to the input image space. Similar to the UNAP, it has the reassemble module. So reassemble module, in reassemble modules, we concat the tokens as a shape of the original tensor and projected to the another field, another domain, another embedding space, and concatenate with the previous output. In fusion module, we fuse this one and this one. This decoded output and the skipped output. So this is the very similar to the FPN like architecture. 피처 피라미드 network like architecture. 그렇죠? 이렇게 컨버전들에서 퓨전을 하면 finally we achieve this depth map looks like this. It's like this. So this is the result by DPT. So dance prediction transformer. So this is a single image or the monocular image. By learning the mapping function between input images and output text, or the color values or color texture to the output depth values, we can achieve high quality depth information like this. So again, we do not use any kind of geometry prior or the multiple images or multi-light condition. We only have we only use this single image to achieve depth information. Kind of this. This is the monocular depth estimation or the knowledge-based learning for the 3D computer vision. I'd like to show you one of the impressive examples of the monocular depth estimation by using the state-of-the-art method. This is a single images. This is the input monocular images without any other multiple images or the other cues. So by using the state-of-the-art mono depth estimation network, we can achieve this kind of depth map. It's awesome, right? So again, this is the input single images. This is estimated monocular depth map. As you can see here, output depth map. So from here, the brighter, the closer. Brighter, closer. So comparing, so even though we only, even though the network only see these single images, by considering the context or the other depth Q, it estimates the 3D information in monocular 3D information. So it not only take a sharp, find a sharp object with edge preserved output with good relative distance between the instances. So yeah, so this kind of result may be better than state-of-the-art multi-view stereo matching or the photometric stereo matching. It's very, very innovative direction, right? So if this kind of paper works very, very well, then you can recover 3D information from any single images you have. For example, like your images or even cartoon or the sketch, you can reconstruct 3D information. So that's why this kind of the monocular depth estimation is one of the popularly studied area nowadays. Yeah. Question. 그래서 지금 우리가 둘째 시간에 보고 있는 게 뭐냐면 결국에 3D 어떻게 2.5D 뎁스를 어떻게 복원할 건가 라는 문제에서 이제 많은 논문들이 나왔는데 많은 방법들이 나왔고 스테레오 매칭, 확장 멀티플 스테레오 매칭 그리고 포토 스테레오 매칭도 있었다가 이제 최근에 결국에 날리지 베이스드 러닝이라고 하는 거는 결국에 어떤 모노큐lar 뎁스 에스티메이션이라고 하는 분야로 온 거고 싱글 이미지만을 갖고도 이렇게 뎁스를 잘 살 수 있다면 정말 많은 어플리케이션이 있겠죠. 그렇죠? 사실 3D 데이터는 다들 알고 있어요. 하지만 3D를 하지 못했던 이유가 결국 3D 데이터의 부재 그리고 3D를 학습하기 어려운 또는 3D를 획득하기 위한 constraint, 멀티비 이미지라든지 멀티플 라이트 소스라든지 constraint 때문이었는데 어떠한 싱글 이미지만 가지고 이렇게 복원할 수 있다면 정말 많은 패러다임이 바뀌었죠. 그렇죠? 그래서 이 그림을 여러분들에게 보여주고 싶어 가져왔는데 최근 스토타 방법으로 이런 싱글 이미지만 보고도 이제는 우리가 3차원 정도 이렇게까지 찾을 수 있더라. 물론 이것도 작년 논문, 올해 초 논문이었고 이제 최근에 나온 논문들은 사실 더 잘 돼요. 그래서 이제 이런 데까지 우리가 와 있다라는 거죠. 결국에 이게 이제는 결국에 2.5D 뎁스를 러닝 기반으로 찾는 어떻게 보면 가장 이펙티브하고 이피션트한 솔루션이겠죠. 그렇죠? Question. 준성아 쌤, unfortunately this paper 이거 논문 레퍼가 없구나. 리얼타임은 안 돼요. 사실 이건 테스트 타임에 약간 옵티미제이 들어가거든요. 그래서 리얼타임은 아니지만 물론 최근에 정말 더 좋은 논문들이 나오기 때문에 향후에는 충분히 리얼타임이 될 수 있지 않을까라는 생각은 들고요. 이 디피트 논문은 사실 리얼타임은 아니지만 어쨌든 피드4 네트워크 한 번으로 이렇게 만들어내긴 하니까 이 비전 트랜스포머의 어떤 악셀레이션만 잘 된다면 빠른 시일 내에 리얼타임도 갈 수 있지 않을까 좀 생각은 드네요. Question. Other question? No? Okay, so this is the 2.5D depth information, depth estimation. So, of course, this is just a 2.5D depth information. So, in fact, this is not a full 3D information. So, to achieve full 3D information in some application, in fact, if you consider the self-driving car, 2.5 dimensional depth information is enough, 그렇죠? But if you want to solve the another application like the face reconstruction or the other things, you may require full 3D information. So from now on, let's talk about how to achieve full 3D information by using the deep learning. Okay. Before then, let's take a 10-minute break. And let me start 37 p.m. 우리 여기서부터 이제 10분만 쉬었다가 3시 37분에 다시 시작하도록 합시다. Let's continue. So from now on, okay. So from now on, let's talk about how to estimate full 3D information. So yeah, here. Okay. So conventionally, the first 3D estimation based on the optimization consisting of the two parts. In first part, learning multiple model from the 3D data, multiple model and 3D data. The multiple model means, for example, if you can see here, multiple model means we can set the model with a controllable parameter. So by controlling the parameter, for example, facial expression or something like this, which was called the modeler, then fit this model to the input image, then estimate the 3D multiple model. So in other words, by adjusting each parameter in our model, we find out the best matches the 3D representation, which is fitting the model to the input images. Then we can finally achieve the full 3D model for this given input images. This is the optimization paradigm for the knowledge 3D information. Similar technique was used in the human 3D construction. So first of all, learning a multiple model from the 3D data. So for example, the SMPM model. So this is one of the most popularly used model. This SMPM model is from parametric 3D representation. These meshes, human meshes, determined by less than 200 parameter. Then by adjusting such kind of parameter, we fit the model to the input images. So for example, given an image, by adjusting our multiple models, then minimizing the distance between these two, then finally find out full 3D model. Of course, because this is the ill-posed problem, so because we only have the single images, we require lots of prior, the geometric prior. For example, the human body, two human leg cannot cross each other, for example, like this. So anyway, so this is optimization paradigm for the knowledge 3D reconstruction. Nowadays, the hybrid method was popularly used optimization solution as a supervision. So in this paradigm, here, in this paradigm, we use the CNN network, which take an input image and output the parametric 3D model, and we use this one as an initial parameter, 3D parameter, and by fitting this 3D model to the input images like this, and finally achieve the optimized shape like this. So this is the hybrid method to estimate 3D model in ICCB 2019. But after deep learning revolution, so most of methods try to find the direct mapping function between the input 2D image to the full 3D model. In this case, the Boxer model. So by formulating this network as a convolutional neural networks in a supervised manner during training, ground truth 3D representation is used to train this CNN module. Then at testing time, we can find out first 3D model from the single 2D images. This is the supervised learning. This kind of technique started in early 2016 in CCCB, something like this. This kind of technique can be used in any representation. For example, like the pixels to meshes, the input image to mesh. We can learn the mapping function between the input image to the mesh model, or the input image to the point cloud model, or the input image to the SCDF, 그쵸? occupancy representation, or what else? This mesh model. There are so many kinds of the supervised learning technique between input image to the 3D representation. For example, mesh, point cloud, impression representation. For example, like SDF. One of the most popular technique is the mesh RCNN, which is very similar to the mask RCNN. So we can say that mesh RCNN is the extension of the mask RCNN to estimate not only segment mask, but also 3D mesh information. Here's a problem formulation. We have an input single RGB images here. Then we want to train a network that outputs a set of the detected boxes. For each box, bounding box, category level, insert segmentation can be estimated. So this kind of information can be estimated by the mask RCNN we discussed in lecture note 2. And in mesh RCNN, we additionally estimate 3D triangle meshes. We can just say that 3D meshes with the additional hat. So this is output of the mesh RCNN. So given a single image like this, we can estimate not only object information, 2D information, but also 3D mesh information at each object like this. This is a mesh RCNN. Let's talk about mesh RCNN. So before talk about mesh RCNN, I want to talk about predicting meshes with a neural network. So as we discussed, this is a kind of the neural net mesh model. So as you can see here, it may be really challenged to directly finding the mapping function between input image to this mesh representation. So in mesh estimation with a neural network, many methods try to use the iterative mesh refinement technique. So in this technique, it starts from the initial ellipsoid meshes, these kinds of ellipsoid meshes for each object. Then the network predict offset for each vertex. I mean the offset for each the network predict the offset for each vertex, then find the mesh deformation to estimate blob mesh information. Then by using the graph neural network, we unpooling these meshes, I mean increase the number of vertex and apply the mesh deformation again and refine again. So this is the iterative mesh refinement module. So yeah, so by using this kind of the iterative mesh refinement module, in mesh RCNN pipeline, given an input 2D images, single 2D images first of all, extract the 2D object recognition information like the bounding box or the mask information, and estimating the 3D object voxels, and finally achieve the 3D object meshes. I can show you here. So similar to the mask RCNOs, it has a box and mask branch to generate the 2D mask and box and class information. But in mesh RCNN, it has the additional branch, voxel branch. In voxel branch, they use the ROI alignment module to extract the this, what to say, the voxel-like input images, input information. So not a 2D box, 3D box. So ROI alignment, this ROI alignment extract the 3D box, and by applying mesh refinement branch, we refine initial voxel-like information as a meshes, first to find meshes iteratively. So graph convolution layer and refinement layer, and find out the coarse meshes first and refine again. I will skip details, but yeah, luckily we finally achieved the corresponding final meshes for each input object images. This is a mesh RCNN. This mesh RCNN. Yeah, this is the result of the mesh RCNN. Given an input object, by using this kind of mesh RCNN technique, we can achieve this mesh information from the single input images. Compared to monocular depth estimation, here we can estimate the full 3D information. So not only we can estimate the steps information for the visible viewpoint, we can estimate the invisible depth information or the 3D information in mesh RCNN method. This is another example. Yeah. So given object, the instance object, this is the novel images or the unseen images, neural network, the mesh RCNN network can generate or the estimate or impact or predict this full mesh model. Comparing to the monocular depth estimation, state-of-the-art monocular depth estimation output, the performance is relatively limited. So I think that this direction is the alternative. It's the alternative. So I think that this direction, the full 3D modeling from the single images, is a kind of a solution. So if you're interested in, I suggest to study this part. So anyway, this is a result on another data set, on fixed 3D data set. So given a scene, arbitrary scene, we can reconstruct each object, sofa, table, chair, or another chairs. We can reconstruct the meshes, full 3D meshes like this. So this is the output of the mesh RCNN. Yeah. Although effective, it has key challenges. Supervision problem. The method we discussed so far based on supervised learning. It means that it requires 3D supervision. It requires 3D ground truth representation. For example, like meshy point cloud voxels, as well as corresponding depth or the camera pose information. For example, extrinsic parameter or intrinsic parameter. Let's compare difficulty to view 2D supervision and 3D supervision. So 2D supervision was like category label or the bounding boxes or segmentation. And 3D supervision was a 3D shape, 3D representation where the camera pose or something like this. 2D supervision can be annotated by non-expert human easily. What about 3D supervision? It is not easily annotated by people. In many cases, you require dedicated hardware to make a supervision, 3D supervision, I mean the 3D ground truth. For 3D recognition to succeed, we must rely primarily on 2D supervision only, not a 3D supervision. So in 3D, key challenge for the 3D, modern 3D computer vision, how to reduce the 3D supervision is one of the essential question to overcome the limitation of the aforementioned issues. This is the current topics in the 3D computer vision. The question: does compute on mesh prediction? Does it also predict the relative position of each object? It's very, very important question. In fact, they did not consider relative position between each instances. So that's one of the most important, one of the critical challenge, because the in 2D representation, for example, object box or segmentation, we do not consider the object relationship, right? Object geometry relationship, but in 3D reconstruction, we have to consider the not only single object geometry, but also we have to consider the different object relationship, geometry relationship. But in this paper, they did not consider this kind of relationship. So in our lab, we want to overcome this kind of limitation by using the something like the panoptic algorithm, but we just failed because there was so many kinds of other limitations. So maybe one day someone will solve those kinds of problem. 그래서 저는 뭐 너무너무 좋은 질문이 맞아요. 그래서 이게 이제 멀티 오브젝트 간의 릴레이션십, 지오메트리 릴레이션십, 즉 얘가 더 앞에 있고 뭐 얘가 뒤에 있고 하는 것들은 뭐 간단한 그 정도 릴레이션십뿐만 아니라 어떤 지오메트릭하게 어떤 릴레이션십이 사실 저희가 못했던 게 사실이고요. 사실 그게 되려면 뭐가 돼야 되냐면은 이런 오브젝트 단위의 풀 3D뿐만 아니라 이 신 단위의 뎁스 인포메이션까지 다 나와야 걔네들의 어떤 파노틱한 3D 컨스트럭션이 돼야 그 릴레이션까지 찾을 수 있는데 사실 정말 챌린지하죠. 그래서 이제 뭐 이런 것들이 사실 요 3D 컴퓨터 비전, 사실 우리가 오늘은 계속 3D 컴퓨터 비전 얘기하고 있는데 막상 말했지만 정말 의미 있는 분야이기도 하지만 아직 2D 컴퓨터 비전에 비해서 unexplored 된 분야임에는 불명하고요. 많은 사람들이 이제 이런 연구들을 하고 있고 3D V라고 하는 3D 컴퓨터 비전에 특화된 뭐 3D V라고 하는 컨퍼런스가 따로 있을 만큼 정말 활발하게 연구되고 있는 이제 컴퓨터 비전 분야 중에 하나이기도 하고요. 개인적으로는 컴퓨터 비전에 가야 되는 방향이 이런 3D라고도 할 수 있어요. 그런 측면에서도 이제 이런 한계들이 좀 해결돼야 되는 가장 큰 이슈이기도 하죠. Anyway, supervision problem is the one of them. So, again, challenges with the supervised learning. They are limited in scales and variety. We do not have the 3D data for the arbitrary images, for example, like the web images. To extract the 3D information, we may require the marker tracker, or for example, like the hardware, or constrain the lab setting, for example, like the fixed camera with multiple camera. Or so in many paper, they just use the synthetic data, rendered data. So it definitely stems from the domain gap, real and synthetic domain gap. And this synthetic data does not look like real data, right? So ecologically unplausible. So the question in modern 3D learning, how to reduce the level of supervision instead of 3D ground truth representation, for example, like 3D model or depth information or the 3D camera pose estimation, pose information. This is the topics of the modern 3D computer vision. What kinds of data can we assume? Multiple images or the single image collection, right? In this kinds of data, we do not have the corresponding 3D ground truth representation, but there definitely exists the 3D cube from the multi-view images or the single image collection that share the semantic knowledge. For example, like the same dog images or the same cat images. Then the question is, what kinds of cube are there? Pixels or the silhouettes on non-correspondences or the non-key point correspondences between multi-view images or multiple images. By using these kinds of cube or by modeling these kinds of cube, we can overcome the need of the 3D ground truth representation. How? Like this. Okay, let's go back to the us. So as a human like us, okay, if you see so many kinds of bird images, if you can see so many kinds of bird images, let's say training data, we can just assume what bird shape are like, right? So okay, so maybe it has the breed here and it has a wings over there, something like this. This is training step, and testing step. Maybe human like us, we can easily expect full 3D information given only these single images, because we already learned many cues from the set of the uncreated 2D images that share the same semantic meaning as a bird. Right? That's the idea of unsupervised 3D reconstruction. So question is how to extract a cube from only 2D image collection. This is the topic of this paper. So learning category specific mesh construction from the image collection in ECCB 2018. How can you do that? Unsupervised 3D reconstruction. How can you do that? Maybe there are so many kinds of possible solutions to extract the cues from the 2D images, but in this paper, they want to use auto-encoding concept. Auto-encoding concept. What does it mean? Disentangling and reconstruction. What does it mean? If we have a single images, we can design a neural network, let's say convolution neural network, and generate camera pose, shape, 3D shape, in this case mesh, and texture information. We don't have the ground truth for this one, but if we have the differentiable render differentiable renderer mean? By using the camera and mesh and texture information, by using the somehow differentiable renderer, we re-render images like this. This is kind of inverse graphics. Inverse graphics. Because in graphics module, in graphics view, there were so many kinds of renderer from the mesh, texture, and camera. 그렇죠? 여러분들이 아마 만약에 뭐냐면 애니메이션 학교면은 애니메이션 이 3D 모델은 있고, 그렇죠? 아, 이게 인버스 그래픽스가 아니라 그냥 그래픽스 모델이죠. 그래서 이 전체가 인버스 그래픽스고, 아마 여러분들이 그 그래픽스 생각해보면은 3D 모델이 있고 카메라가 있고, 카메라 원하고자 하는 카메라 뷰 포인트를 주고 텍스트를 주면 이런 뷰에서 보는 카메라 이런 모델을 만들어야잖아, 렌더러가. 그걸 이제 우리가 디퍼런셔블하게 모델링 할 수 있다면, 그렇죠? 네? Question is, does the rendered image look like input? So if these neural networks were trained well in this procedure, this input image should exactly same to these reconstructed images. So, in other words, by using this kind of loss function, this kind of loss Q, similarly between the input images and the reconstructed images, we can train this convolutional neural network. And testing time, by using this network, we can estimate the 3D information as well as the camera port and the texture information. This is the very, very straightforward unsupervised 3D reconstruction method. In practice, reconstruction is not enough because the quality of this 3D information is not enough. So this works use a key point, not a input pixels values. But in this paper in ECCB 2018, the proposal relatively is good, as you can see here, like this. So these reconstructed meshes are not based on first 3D model. This one just learned from the image collection with the same category specific image collection, bird, motorcycle, shoes, cars, something like this. By using disentangle and reconstruction framework. This is the unsupervised 3D construction method. Any question for this paper? 자, 뭐 여러분 이해되죠? 그럼 여기까지 보고 갈까? 잠깐만. 이해되죠? 그래서 어떻게 하는 거냐면 우리가 이제는 계속 이제 슈퍼비전 문제니까 어떤 2D 이미지 컬렉션들만 가지고 3D를 찾는 네트워크를 학습하고 싶은 건데 어떻게 할까를 많이 고민을 했었겠죠, 사람들이. 그래서 어떻게 했냐면 disentanglement and reconstruction이라는 파이프라인을 생각해낸 거예요. 뭐 하냐면 이미지로부터 뉴럴 네트워크를 통해서 카메라의 포즈와 쉐입과 텍스처를 디센탱글링하는 네트워크를 디자인한 다음에 그 네트워크 아웃풋을 가지고 어떤 어차피 백프로포션 돼야 되니까 디퍼런셜 빼야겠죠? 디퍼런셔블한 뉴럴 렌더러, 디퍼런셔블한 렌더러, 그래픽스에서 많이 연구되었던 렌더러를 사용해서 인풋을 다시 한번 복원을 했을 때 이 복원된 것과 인풋이 같아지도록 로스를 흘려주면 우리는 이 네트워크를 without any ground truth 3D information으로 학습할 수가 있다라고 하는 이런 개념들이 이제 나오기 시작했죠. 18년도부터. 이러한 컨셉을 가지고 이제 많은 방법들이 발표가 되기 시작하죠. 저는 the category used as a conditional input. Not exactly. So in this paper, they trained the network and object category independently. So each convolution network is trained on category specific object independently. So they did not use the conditional. They didn't use the category as a conditional input. Okay. Okay. So we can generalize this framework as a unsupervised shape prediction. Unsupervised shape prediction. Like this. Input images. We can design the CNN image encoder, and we can design 3D shape decoder. 그렇죠? In this case, mesh. 그렇죠? Mesh. Then, by using the differentiable silhouette renderer, we may reconstruct these silhouette images, binary images, and if we have input corresponding true silhouette images, this one, by minimizing the distance between the predicted silhouette and true silhouette, we can train both CNN encoder and 3D shape decoder. This is the general framework of the unsupervised shape prediction or the 3D prediction. But in this kind of framework, we have a critical problem. 3D shape and 3D shape is ambiguous from the single view. For example, there are two different 3D models, but if we see the two different 3D models from this viewpoint, this single viewpoint, this 3D model will generate same silhouette even though they have a different 3D shape. So this is the ambiguity. 3D ambiguity. So how to overcome this limitation? So in many papers, they use another view or second view during the training. So like this. So from these images, we reconstruct the shape here, and by using the known camera pose, we moved camera viewpoint here and render original view and another view and extract the predicted silhouette here and here. If we have original view silhouette and another view silhouette as a supervision, we can better train this network. I mean, we can overcome ambiguity problem because we can consider another viewpoint to train this network. So this additional other view supervision, silhouette or the images can help to overcome the ambiguity problem. So in this kind of technique, supervision, we have the input images and corresponding mask and another viewpoint mask with the camera viewpoint. So by using this set of the supervision, we can train the better 3D reconstruction model without any ground truth 3D model. So this is the unsupervised shape prediction pipeline in CBPR 2020. Question. We will skip how to shape prediction architecture, how to formulate the 3D shape prediction. So in this paper, similar to the mesh CNN, they use the vertical alignment, graphical motion with respect to the mesh structure. But if you are interested in, please read this paper. We'll skip this one. But this is the output of this method. Given these input images, single input images, estimated 3D shape, trained without any 3D supervision, the output is relatively good. When we see this 3D model in different viewpoint, the 3D ambiguity was the highly reduced here. So anyway, this is the unsupervised shape prediction paradigm. Okay. Question. question? No? Okay, so far we discussed how to reconstruct the 3D, full 3D with and without 3D supervision. At the beginning of today's lecture, we discussed the neural. So far, this one just consider the mesh representation or the expression 3D representation. But as we discussed at the end of today's lecture, nowadays in-person representation has been pervasive. The novel business is one of them. So from here, we will talk about nerve, neural radiance field, and see application of the neural radiance field. Question? No? I think okay. I think we can finish today's lecture here. And next week we will talk about novel synthesis and neural radiance field and nerve. Okay, and we will see paper presentation. So again, we will, so from next week we will increase the paper 7 time as a 10 minutes per paper, reduce the code review as a 10 minutes per paper. So yeah, please prepare your presentation. And if you did not present yet, please apply on our Google Sheet. You may get a chance to present. Yes. Okay. 지은 학생 질문이 반영이 안 돼 있어요? 미안해요. 제가 확인해 볼게요. 네. 메일로 준 친구들은 반영이 안 됐을 수 있을 것 같아요. 제가 메일 받았으니까 반영할게요. 알겠죠? 오케이. 더 질문이 없으시면 우리 오늘 여기서 끝내기로 하고요. 시간이 정말 빠르죠? 그쵸? 우리 이제 한 2주 정도 더 보면은 기말 보고 이제 2학기 마무리하는데 여러분 이제 마지막까지 조금만 더 힘을 내서 가보도록 합시다. 오케이, 오늘 여기까지 하고요. 우리는 다음 주에 보도록 합시다. 고생하셨습니다.